All right, so today we're going to be talking about vertex form of quadratics. So as you know, a quadratic function, the parent function looks like this, where we have that x squared term. And usually we see this in what we call standard form, which just sort of looks like this. It looks like x squared plus x plus some sort of constant c. But there is another form that we can write this in, and that is called vertex form. Now, this vertex form should actually look really familiar because this is the type of form that we saw when we were talking about transformations of functions. We had our up and down movement here, and we had our horizontal movement here. Now, the way vertex form works is it uses that horizontal movement, this h term here, and it uses this k term here, this up and down movement, the vertical movement, to give us our vertex. Because if you recall, when we were transforming parent functions, we were physically moving our parent function around the coordinate plane. We were moving that vertex. This is just another way to write that. And again, the big bonus here is that it actually gives us the vertex of our parabola. This means that we can automatically take our h value, our horizontal movement, and plug it in right there as our x value in our vertex, and our vertical movement, our k value, becomes our y value in our vertex. So again, just a quick recap from our transformations of functions unit. This a value here, this value outside the parentheses, tells us how much our graph has been either stretched or compressed. It's our scale factor. Our h value right here is telling us our horizontal movement. So it's telling us how we're moving left to right. And our k value is going to tell us our vertical movement. So if we have some sort of function like this, I can use this information from my standard vertex form to pull apart what my graph is going to look like. For example, in this one, I have an a value here of 2, which means that this is going to be stretched by a value of 2. This 2 is also positive, which means that this is going to be facing up. It's not reflected. Our h value here is 1, which means that I've moved 1 space to the right. And my k value is -3, which means that we've moved 3 spaces down. So if I think about what that actually looks like on the coordinate plane, I've taken my vertex from 0, 0, and I've moved 1 space to the right and 3 spaces down. So this is the vertex of this particular function. Let's take a look at another one together. So for this one here, we have g of x is equal to -1/2 x plus 2 squared. So my a value here is -1/2. And this tells me a few things. It tells me it's being stretched by a factor of 1/2. And because it's negative, it's going to be facing down. It's been reflected over the x-axis. I also can see that I have an h value of 2. And this is actually an h value of -2 because, if you recall, our vertex form has that x minus h, and this one happens to be positive. So our h value here is going to be -2. This means that we've moved 2 spaces to the left. You'll also notice that there is a piece of this that is very conspicuously missing. I do not have a k value, so that means that my k value is +0. This isn't being moved vertically at all. So what does that mean for us in terms of our vertex? Well, it means that our vertex, we've moved 2 spaces to the left, so our x value is going to be -2, and we did not move up and down at all, so our y value is going to be 0. Pause the video, see if you can do the same thing for this h of x down here, where we have h of x is equal to 3x squared minus 1. In this one, our a value is 3. So this is going to be stretched by 3 by a scale factor of 3. It's also positive, so it's going to be face up. It's not being reflected. I'm noticing that it looks like I'm missing my h value, because if we had an h value, we would have our parentheses. It would be, attached to our x by a plus or a minus. We don't have that. So that tells me this is not being moved horizontally at all. Our h value is going to be 0. That being said, we do have a k value. We have -1 right here. So that means that we are moving down by 1 space. So the vertex for this particular function is going to be 0, -1. All right, so let's take some time to see how we can use all of this information to help us graph and identify some key features of our quadratics. So starting off strong, we have our vertex form here. We have 2 times x minus 3 squared minus 2. So we can very quickly identify our h value and our k value. So our h value is going to be 3, and our k value is going to be -2. So this means that the vertex of this particular quadratic is going to be at 3, -2. And so we can go and plot that. Now, this is super helpful because of the next point, which is what's called our axis of symmetry. Now, our axis of symmetry is this invisible vertical line that goes straight through our vertex. And the equation of this particular vertical line is going to be x is equal to whatever the x value of our vertex is. So in this case, it's going to be x is equal to 3. The reason it's helpful is because any point that's on one side of our axis of symmetry is mirrored on the other. Remember that all parabolas are symmetric, and so they are identical on either side of their vertex. So, for example, knowing that my vertex is at 3, -2, why don't we plug in the number 2 and see what point we get? So if I plug in 2 for x, 2 times 2 minus 3 squared minus 2. 2 minus 3 is -1, so I have 2 times -1 squared minus 2. -1 squared is just 1. 1 times 2 is 2, so I have 2 minus 2 equals 0. Okay, so I plugged in the value of 2 for my x, and I got 0 as my y. So that means there's a point here. But because there's a point here, there's an identical point on the other side at 4, 0. And we could go through and actually prove that to be the case. If we plug in 4, we'll have 4 minus 3. And then that once again gives us 1, and the whole thing sort of plays itself out again. Let's get one more point for the purposes of plotting this. Let's see. We plugged in 2, so let's plug in 1 and see what we get. So 2 times 1 minus 3 squared minus 2. That's going to be 2 times negative 2 squared minus 2. Negative 2 squared is positive 4, so 2 times 4 minus 2. That's going to be 8 minus 2, which is equal to 6. So I plugged in 1, I got 6, so I can now plot that point. So 1, 6. 1, 2, 3, 4, 5, 6. And again, because of my axis of symmetry, this point is going to be exactly mirrored on the other side. And so we get this idea of what this graph looks like just by choosing a couple of points to plot. So here we go. So again, we can see, here's our vertex. It's at 3, negative 2. Our graph is facing up because that A value in front, that 2, is positive. And you can also see that it appears to be stretched. And that's because our A value is 2, so it's being stretched by a scale factor of 2. Our domain and range. Our domain for parabolas is always going to be the same. Our domain is going to be all real numbers. So we can say x such that x is a real number. But our range does have a restriction. Our range, if we're looking at it, does not have any values below negative 2. That's the lowest point on this graph. So our range is going to be y values such that y is greater than or equal to negative 2. Here's one for you to try. Pause the video, see if you can identify the vertex, the axis of symmetry, try and graph it, see what you get for the domain and range. So for this one here, we have 4 as our h value, and it's x plus 4, which means we're dealing with a negative 4 as our h value. And we have negative 5 as our k value. So that means that our vertex here is going to be at negative 4, negative 5. And if our vertex is at negative 4 or negative 5, our axis of symmetry is going to be x is equal to negative 4. So let's start by plotting our vertex. So negative 4, negative 5 is going to be down here. Now the first thing that I'm noticing, now that I've done that, is that my a value is negative 1. I have that negative sign sort of camping out front. That tells me this parabola is going to be facing down. So just something to keep in mind. So I had to deal with negative 4, so I'm going to plug in, let's say, negative 5 to help me get my next point. So let's do that. F of x is equal to negative, parentheses, negative 5 plus 4 squared minus 5. Negative 5 plus 4 is negative 1. And then negative 1 squared is going to be positive 1. That negative outside is going to flip that to be negative again, which is going to give me negative 6 for my y value there. So negative 5, negative 6 is a point. Now, again, because my axis of symmetry is going straight through my vertex, this point is mirrored on the other side. So I can just plot that one without having to go through all of the substitution over here. Let's do one more. Let's plug in, well, we just did -5, so let's do -6. So, -6 plus 4 squared minus 5. So, -6 plus 4 is -2. This is going to become +4, but that negative is still hanging out front, so that becomes -4 minus 5, which is -9. So -6, -9 is a point, which is here, which means it's mirrored on the other side over there, and so my parabola is going to look something like this. Now taking a look, like we said before, our domain is always going to be all real numbers for parabolas, so we don't have any x restrictions there, so x is a real number, but our range does have a restriction. So if we take a look, the highest point on this graph, the highest my y value goes is -5, so I'm looking at y is less than or equal to -5. Now there's one more thing I want to talk to us about is how do we write the equation of a parabola if we don't know all of the information about it? Well, as long as we have the vertex and one of the points, we can actually write an equation pretty easily. So let's take a look at this idea. What about if we had a vertex of -2, 3, and a y-intercept of -1? Well, first things first, we know, using our vertex form here, that we can plug this information in. So let's start with that. F of x is equal to, I have absolutely no idea what my a value is, so I'm just going to write a for now. I have x minus -2. I'm going to flip that over to being positive in a second, plus 3. So if I want to simplify this just a little bit, I have this. A plus, there we go, plus 3. Okay. Now, because we know that the y-intercept is -1, we know that if x is equal to 0, then y is equal to -1, and that's because 0, -1 is a point on this particular parabola. So what we're going to do is we're going to just plug this information in for x and y. So -1, because that's my y value, equals a times 0 plus 2 squared plus 3. Now I've limited it down to just one variable. Let's solve for a. -1 is equal to a times 2 squared plus 3. So -1 is equal to 4a plus 3. I'm going to subtract 3 from both sides. I'm going to end up with -4 equals 4a, which means that a is equal to -1. So that means that our final equation here is going to be f of x is equal to -1 times x plus 2 squared plus 3. And if you wanted, you could drop the 1 there and just make it negative x plus 2 squared. But just for the purposes of this exercise, I wanted to show you where that went. All right, here is our next sort of you try it. Write an equation for a parabola with a vertex of 1, -4 that passes through the point -2, -1. Pause the video, give it a try, and then come back and check your answers. So I'm going to start by writing out my vertex form, and I'm going to plug in my vertex. So I have f of x is equal to a times x minus 1 squared minus 4. So far, all I have done is I have plugged my vertex, this right here, into the vertex form of my equation. Next, I am going to substitute in the 2 values right here from my second point that I was given. So, I know that -1 is the result if I plug in -2. And so that's going to be what this looks like. -1 is equal to a times -3 squared minus 4. So I'm going to have 9a minus 4. Add 4 to both sides. I'll end up with 3 is equal to 9a, which means that a is equal to 3 over 9, which simplifies to 1/3. So my final equation here is going to be f of x is equal to 1/3 x minus 1 squared minus 4. I look forward to practicing with this with all of you next class.